All right. Angular momentum. Actually, no, I'm not going to start with angular momentum. I'd like to talk about another thing before we get to angular momentum, because I haven't really fully discussed how would you determine the rotational inertia of something that doesn't have these nice symmetrical shapes? Because, everything is like so nice, like all these nice, beautiful spheres and cylinders and rods. Everything's so nice. Or if you cut it in half and compare the halves, they pretty much look the same. You just got to flip one of them over. Symmetric, of course, is what we would call that. And let me see. Let's see. Yeah. Fine. How do we figure out the rotational inertia of something that's not symmetrical? I don't know. Let's say my coffee cup. No, not a good example. Let's say it's this. What is the rotational inertia of my soap bottle? And they very well might ask a question, an experimental question on the AP exam right along this line. They're going to give you some strange object and have you talk about how would I determine the rotational inertia of my soap bottle? Well, first I'd have to determine an axis that it's rotating through. If my axis is, I guess I could reference the axis with a pen or pencil. If the axis goes this way, if the axis is going like this, then this thing is going to be flipping like this. Or if the axis goes straight through like a skewer, just taking it and just jamming it right through the bottom, like right along the spine, then this thing is going to be rotating like this. How would I figure out what the rotational inertia of it is once I've determined what my axis of rotation is? You're not going to be able to find an equation online for the rotational inertia of the soap bottle. And we would all agree that's an outrageous idea that there would be an equation online for the rotational inertia of a soap bottle. So how would you do that? Does anybody have any ideas how you would experimentally? It's only done experimentally. Anybody have ideas as to what kind of experiment you could do to determine the rotational inertia of some strange object? All right, well, I will tell you what we would do. Let's just give an example of, I don't know, this is my strangely shaped object. Unusual shape, unusually, that's not the correct word, unusually, I don't know. Unusually shaped object. Non-symmetrical, I mean, I guess that's textbook would say non-symmetrical. A non-symmetrical shaped object. What would we do? Well, technically, what you would have to do is maybe set, and assuming that the axis of rotation, let's just assume that the axis of rotation goes straight down like this. Then you'd have to build something. You'd literally have to take some sort of, I don't know, drill and drill a hole through it. So you would drill a hole through it and you'd have to have some sort of base. And the base just holds this up. You push this physical thing straight through it. I mean, this would be difficult. I mean, I'm just giving you the general idea. In the real world, there'd probably be a bunch of friction in there. And when you try to spin it, it won't even spin. So, I mean, you would have to really carefully, create this. But there's science labs that have systems that are like this, that they can put other, unusually shaped objects into these things that they've used a lot of money to create, and it works. So what do you do from here? So essentially, again, you build an apparatus that you can mount the object on. You pierce some sort of axis through it so that it can rotate. So it's free to rotate. Free to rotate around the axis, right? Then what you would do is you could take a rope and wrap a rope in fact, now that I think about it, this is probably not the best way to do it. It'd probably be better to say doing this sideways makes the most sense. I mean, you could do it either way. You would pull, I'll just continue with what I'm doing. And you would pull the rope with a constant force. As you pull this rope that's been wound around it, it will start to rotate. Right? This thing will start to rotate because you start by wrapping this rope around it, presumably with negligible mass, because you don't want to add extra rotational inertia to it. If your goal is to determine the rotational inertia of this object, then it would have to be something thin, which would be easy to do. A string would be pretty straightforward. And then you would pull with a constant force. As you pull, once this begins rotating, time how long it takes to complete X rotations. I mean, it could be any number. I mean, one might be difficult. If you're pulling really hard on it, it might be like, start, stop. I mean, and you wouldn't even want to use a stopwatch. You would want to use a computer like we have with Pivot so that you could accurately time it. But once this begins rotating, time how long it takes to complete X rotations. You could do 10 rotations if you wanted to, and then divide by the time for 10. I mean, that's a reasonable way to do it to avoid error. And that will give you the period, right? That will give you the period amount of time for one rotation. So you get the period. You get the period of rotation from this, which is the time for one rotation. And remember, this thing would be accelerating. This thing would have, if there's a constant force on a box, as you push it across the floor, then it's going to accelerate. It's going to gain, it's not moving at a constant speed. This thing would presumably have a pretty low friction axis that you've built. So it will actually spin, but gain rotational speed at a certain rate. So note, this force, this would create a constant acceleration. This would create a constant angular acceleration, just a note. And you'd have to measure this force. You'd have to measure this. You'd have to measure how much force you're applying. You have to measure how much constant force you're pulling with. You'd have to have your stopwatch to time how long it takes to go through let's just say 10 rotations. And then you'd have to think about how is this rope getting torque? Well, technically the rope's getting torque because R actually goes from here to here. And then the rope, remember, and it's hard to draw like with depth, but it's not really different than the idea of a pulley. If a pulley is going like this and R goes like this and the rope is pulling down, then the distance from where the rope is applying the force and R is like this. So there's actually an R. You'd have to measure R, right? And so the torque, you'd have some physical force. It's hard for me to draw that. I don't know exactly how, but there is an R in there. And so the torque from the rope would be, the torque from the rope would be R times how much force that you're applying to it. That would be the perpendicular force. So you're controlling this experiment. You're setting it up so it can spin. You're pulling with a certain force that you can measure. Maybe use a spring scale, or if you're more sophisticated stuff in your lab, you would use some tool that as you pull it, it shows how much force you're pulling with. You have your timer for measuring, because you're ultimately going to have to think about the time aspect, because if this thing's accelerating, you're going to need to be able to know what is the rate, what is alpha, what is the rate that the rotational speed, which is omega, increases per second. So that's the general idea. Again, you pull it with a given force, you measure the force. If you measure r, which is technically the radius again, right in here, then you can determine the torque created by that rope. So torque, check. Alpha, you're going to have to work out, because we would be utilizing torque equals I alpha. Again, I'm trying to give you a description of how someone would experimentally determine I for some strange object. Well, if you can set something up like this, where, again, torque is a measurable thing and you can control it by applying a certain force and measuring R where it's wrapped around the object. You can get torque, check. You can get alpha from the timing mechanism and using some kinematics equations for rotational motion. As long as you got the time, you know each revolution is 2 pi radians. Then technically, I should be whatever torque you applied divided by alpha, right? Technically. However, they wouldn't want you to do that. They'd say, well, that's not a very, accurate. When you do more, trials, and you'd say, yeah, you'd actually do a whole bunch of trials. And that's the next part I'm going to point out. Technically, if torque is equal to I times alpha, if you put alpha on this axis, which is in radians per second squared, and you put torque on this axis, which is meters, what should the shape of this graph be if I did it 4 different times? In the next trial, meaning I'm going to leave the rope there, but in the next trial, I'm going to pull with an increased force. Still a constant force. While I pull, it's a constant force, but it's just more than the first trial. Well, alpha should increase, right? If I pull with more force, this thing should wrap around, unwrap itself and rotate more quickly, right? More torque because of the more force, more angular acceleration. That's trial 2. Trial 3, pull with more force, more angular acceleration. Make sure you time it. Write it all down. Trial 4, trial 5. Each time increasing the torque, measuring the increased acceleration for that trial. And then you've got your data. You would have a data table, right? You would have torque, you'd have alpha, and you'd have all your different trials, whatever amount that you decided to do. And then you decide that you're going to plot them. What would the shape of this be? What should the shape of this be? Looking at this formula. If this formula is true, which it is, what should the shape of it be? How is torque related to alpha? They're directly proportional to each other, right? I know that's weird to have 2 alphas again. Notes discovered that the other day. Torque is proportional to alpha, right? And anything that's directly proportional, 0 torque, 0 alpha, 0, 0 makes sense, right? 0 torque, no angular acceleration. But if they're proportional from that point forward in the experiment, then they're gonna be linear, right? They would fall along a line because they're proportional to each other. This is in the format of y equals mx plus b, which of course is 0, because that just indicates if you have no torque, you get no acceleration, right? What would the slope of this be? What would the slope of this graph be if this is true? If torque is on my y-axis, alpha is on my x-axis, then what will the slope m be? It's the rotational inertia. I is the slope. I is the slope of this graph. That's an important idea for you to know. It might turn up in an experimental problem. It has in the past. I don't know how long ago, but I've seen it. I've seen it turn up this exact same problem and actually give the data tables and sometimes even make you graph it. And you don't have to worry about linearizing the data, which is nice because it's already linear. They're proportional to each other. My last comment is relating to just the kinematic formulas, right? Technically, just remember that you would have had, take that back, trying to think theta equals 1/2 alpha t squared. So this is the formula you would have used to get alpha. Just pointing that out if it wasn't clear. Remember that theta is just some rotational angle. So if you just put in 2 pi radians in for one, which is one rotation, the number 2 pi physically goes there, then this would just be the period, right? You would just stick the period in here. And how would you have gotten the period? Well, if you'd let it rotate 10 times because it was just too hard to time it for once, if you were actually doing it with a real stopwatch, you would try to do it for 10 times and divide by 10. And that would have been the period, rotational time for one cycle. And the period would have gone in there, right? And for t, 2 pi goes in for theta. And you would just algebraically solve for alpha. And that number would then go right there. And you would have repeated that experiment, repeated that calculation for all the other trials in the experiment, plotted them out. Slope of the line is the rotational inertia. And scientists actually use this procedure. This is exactly what they do in a much more sophisticated way, but the concept of what I've described is exactly how it's done in the labs. I know that I'm short on time, but I'm going to try to squeeze one other thing in. Rotational momentum, as if you hopefully watched my video from the other day, from last night, you have to know now that, I don't know why that's a really long L, that L is the symbol for rotational momentum. So like we knew in the past, P is equal to mv. For linear, this is linear momentum. So for a rotational momentum, the symbol L is the replacement. And this replacement for m is the rotational inertia, and the replacement for v is omega. So L equals I omega is used as long as you know this thing is rotating and you know what its rotational speed is, which could be increasing. Like for the balls rolling down the ramp, omega keeps increasing, right? Omega versus time has to be linear, right? That's like saying in the old days, v versus t is linear when something is accelerating at a constant rate, and the slope of that is acceleration. Same idea, right? Slope of omega versus t is alpha. So my point is it could be moving at a constant rotational speed, or like in the case of the ramp, it's omega is actually increasing. If someone said, freeze the video in this frozen moment of time, the instantaneous, what is the instantaneous omega? Well, you could do some lab to figure it out, I'm sure, some calculations. But if you knew that omega, you could multiply it by I and know exactly what the rotational momentum is of that rolling object in that moment of time. It's a simple multiplication. Lastly, I'd like to point out for something that is spinning, which I only can do this. I have the setup to do this myself, but I need somebody to spin me. But I did talk about it. I talked about this idea that the spinner, the skater rather, speeds up in their rotation when they put their arms in and then slows down. So you need to know that that does not change the total momentum. The rotational momentum stays the same because there's no interaction with anything outside of herself. That's just a movement of her own arms. And so the angular momentum before her putting her arms out has to be equal to the angular momentum after she brings her arms in. This is like a statement of conservation of momentum. It is exactly that. It's the conservation of rotational momentum. And so what that means, in my last moment, I know I'm almost out of time, is that when you set up these formulas like this, the I, that the rotational inertia she has before, times her rotational speed before she moves her arms out, will be equal to whatever her rotational inertia is after she moves her arms, presumably in, times whatever, this would be after she brings her arms in, times whatever her rotational speed will be after she brings her arms in. This is how you set these problems up. So if they give you information about how I is changing, and you can technically calculate I, we've gone through a lot of examples of calculating I, and if you knew what the rotational speed is before, they usually give you all of this information, and their question usually is, what will the rotational speed of this object be after, some of the mass is brought towards the center? We know it rotationally speeds up, but you can actually solve for it. Using this. All right. At least I can say I'm done with. I had to do that other part, rotational inertia, because I do know that comes up on the exam. And you guys, if you got a question like that, you probably wouldn't even have a shot at it. At least you have a shot at it now. Just know that over the break again, I am going to be providing more on this. That's where we're at right now. I'm going to be providing more on rotational momentum, a little bit also about rotational energy. I hope to only have to do maybe 2 lessons on that. And then I'll be providing also some stuff for simple harmonic motion, as I said to you guys in the past, which is mass spring systems that move back and forth. And my hope is that whoever puts in that effort, I hope you all do, you'll be done with the course. And then we'll have a whole week and a half, actually. When you come back, which gives us that week and a half, we can spend 2 or 3 days, or 1 or 2 classes, I guess, talking about simple harmonic motion. But then at least we'll have 1 full week where the course is done, and you guys can spend the whole last week. I hope you're already starting to review. Again, this is the AP Physics 1. I just bought it the other day for $13 on Amazon. I would highly encourage students to consider getting it. I probably will post some of this, at least in terms of its practice exams that are available. It has 5 practice exams, full solution guides with all the steps and everything for all the parts. And it's very good at summarizing all the most important things that are specific to their exams. They're pretty good at it. They've been doing it a long time. Again, I would highly recommend it. You can buy it on Amazon for $13. You can go to Barnes & Nobles and get it for $20. I'd recommend it. Other than that, it's 10:10, so we're out of time. I hope you guys all have a great and wonderful break, even though you will be hopefully doing some physics. But what would a break be without physics? I can't tell you how many breaks I had while I was in college, where the whole entire break I was just doing work. But if you're serious about school, and that's going to prepare you very well for the college years ahead, for sure. Hope you all have a great break. Enjoy it. I'll see you guys when we get back. Bye, everyone. Bye, everybody.